Part B. Yeah, the topic here, you can see existence and uniqueness of solutions. Yeah, here you can see in this part, we need to learn in the theoretical part. Yeah. For this class, our main focus part is at the problem solving, do computation. Yeah. So not at the theoretical side, but we need to have some, important small portion of theoretical understanding. Yeah. So this part we need to understand these two important questions: existence of the solutions and uniqueness of the solutions. Yeah. All right. First, let's look at a special type of equations, second order linear ODEs, but it's a special type. So Euler-Cauchy equations. Yeah. So the form, basic form, yeah. So look at the basic form here. Yeah. X squared times y double prime plus a constant times x and y prime plus b constant times y. Yeah. Here you can see this equation is very special. Yeah. Yeah. So there is some physical background behind it. So, but when we look at the equation, you can see the coefficient part of y double prime x squared. Okay? The degree 2, double prime degree 2. Yeah, see the special property. Then x, yeah, exponent 1, then y prime. Yeah, first order derivative, then no x. Yeah. But you have y. Yeah. So this property results in another convenient property we can use in problem solving. Yeah. All right. So now let's look at the solution. So in the solution here, yeah, because here you can see, yeah, x square monomial, right? The coefficient. Also monomial. See? Yeah. Monomial, and here we like to choose the structure of our solution y in this special form. This form may not be monomial, okay? Yeah? This form may not be monomial. This form, we call it a power function. So what's the difference? Monomial and a power function. When we talk about monomials, the exponent must be non-negative integers, monomial. Okay? But here, the power function, m is not necessary integers. Could be real numbers, could be any number. M could be complex numbers. Any number, okay, allowed. Yeah. Yeah. So that's why. So it's a power function form. Yeah. So if we choose y in the power function form, then we can take advantage of the special structure of the property I just pointed out. Yeah. Why? So here, let me show you why we can take advantage of the special structure of this equation. When we take the first derivative, y prime, you can see we bring down the power function, the exponent number, we bring down by 1. Okay? We bring down the exponent number by 1, m minus 1, based on the power rule, right? The power rule of derivatives. After you bring down it by 1, you multiply x, so you make it up, right? you bring it back to again, right? Yeah, so the same exponent number as other terms. Similarly, when we take a double prime, y double prime, we bring down the exponent number by 2. Okay? Yeah, by 2. Then you multiply x squared, you bring it back to the original exponent number. Yeah. That's the reason we take advantage of the special structure of the equation. Yeah. Then you can see all three terms, their exponent numbers for the power function part, the same, right? Same. So you can factorize the common factor. Yeah. Now you can see we can factor out the common factor x to the n for all three terms. Then, after the factorization, you can see inside the parentheses, you just have an algebraic equation. Algebraic equation. Okay? Yeah. So when you look at this new form of the equation, all derivatives are gone. Right? You don't have derivatives anymore. Okay? Yeah. And the power function x to the n, you can, yeah. Because this function in general is non-zero, right? Yeah, only it takes 0 at the 0 point, 1 point, just 1 point. Other than this point, non-zero. Yeah, yeah. So then you can consider the auxiliary equation. Yeah. Auxiliary equation we call characteristic equation before. Yeah. Here, this parenthesis part, algebraic equation. M, we treat M as variable. Yeah. So little a, little b, they are known constants. Known constants. Yeah. So we assume we have the values of little a and little b. Yeah. And m, that's the roots of this quadratic equation. And it could be any number, right? Yeah. So now you see it's not necessarily integers. Could be real numbers and it could be complex numbers. Yeah? Okay? Yeah. All right. Then next, we apply the quadratic formula. We get a M1 and M2. I should use this side. Yeah. So, yeah. Oh, why I cannot come? Yeah, because if I use that, freezes, right? Yeah. Oh, yeah. Okay. Yeah. After we get a little m1, m2, then we are ready to write the solution. Yeah. Solution. But when we write solutions, remember, we need to write a y1 solution and a y2 solution. Two special solutions first. Then we do linear combination. All right. So there are three cases, 1, 2, 3. The first case, this quadratic equation has two distinct real roots. Yeah. Two distinct real roots, that is under the square root. The whole number under the square root must be positive, strictly positive. Yeah. Okay, this condition. Then, two distinct real roots. Right. Then we can write y1, y2 immediately in the form, remember, power function form, right? Power function form. X to the m1 for the first solution. And y2, another power function form, x to the m2. Yeah. Two real numbers. So this case, very simple. Yeah. Then the second case, this equation, this auxiliary equation has real double root. Then the number under the square root must be 0. So that's this condition. In this situation, yeah, then our two solutions, y1, y2. Yeah. And here we use little n represent the real part. Yeah, actually, yeah, we can say the real part, but the square root equals 0. Actually, it's gone. Okay? In this case, the square root is gone, so we only have the 1/2 times parenthesis 1 minus a little n, that notation. Okay? So y1 equals n to the n, x to the n. Yeah. Real number. Yeah. Then y2. This time y2. y2. Okay? Yeah. So it must be different from y1, right? It must be different from y1. Okay? All right. Second, yeah, let me write y2 first. Then I explain why we get this y2. All right. y2 equals y1 times natural log of x. Can you see why? Yeah. Can you see why? Yeah. First the y1, but the y1 part we can understand, right? Yeah, a little bit. Yeah. But why natural log of x? That part not easy to understand, right? Yeah. Yeah. All right. Yeah. Okay. Yeah. Yeah. So here, let's use this way. Yeah. We learned one special method last time. Yeah. So let's recall. So we learned one method last time, reduction of order method. Yeah. We have a method we can bring down the order of ODE from order 2 to order 1. There is a method. Okay? So how do we bring down? We need to know y1 first. You need to have y1. All right? So then your y2, remember, we choose y2 equals u times y1. In this way, we can bring down, yeah, because we use a new variable u and a new ODE regarding this u function. And remember, let me remind you, if we let v equals u prime, we can get a first order ODE for this little v function. Yeah. That way, okay? Yeah? So we can use that way, we can find a y2. How about that? Okay? All right. Yeah. So that's the idea. Yeah. But here, I don't want to do that part, yeah, because I may need to use at least 10 minutes to do it. So, but I can put this part in our 2B, yeah, there's a 2B further explanation number 1. Okay? Yeah. So I can explain it. Yeah, just to do this part. Yeah. Calculation. Yeah. And to see if we can get this solution. Okay? Yeah. All right. That case number 3, this time 2 complex roots. Then the number on the square root is a negative number. So we will get an I, right? Yeah. So in that situation, yeah. So here, all right. So then we need to introduce another, symbol, omega symbol, to represent this big square root expression. Yeah. So we want to have a simpler expression for the roots. Yeah. Then, yeah. So in that case, yeah. So we can represent after omega, right? So the real part, we still use this M notation. The real part, in case 3, we use M notation. Then the complex part, yeah, here you can easily see, we can write, for case number 3, we can write M1, yeah, so this case 3, M1, just M plus I omega, right? Yeah, I omega. M2, M minus I omega, okay? Yeah. In this case, yeah. So first, let's write a straightforward version of Y1, Y2. But that straightforward version contains I, yeah, I symbol. Yeah. So in our final solutions, we don't want to include that I symbol. So we want to avoid it. Yeah. So here I use the Y1 star. Yeah. Y1 star, you know, that's not our final form. Yeah. You know, temporary form. Yeah. All right. So the Y1 star, we can write in the, you know, things like this. Okay. Yeah. You know, just put there complex number. Put it at the exponent location. Yeah, we have this. All right. Y1 star and Y2. Okay? Yeah. All right. After that, yeah, because this equation, homogeneous second order linear ODE, it has the linearity principle, right? It follows the linearity principle. We can do plus, minus, you know, linear combination. When we do appropriate linear combinations, we can get around. We can get around the I part. Okay? Yeah? Yeah. All right. So the final version, I is gone. Yeah. So Y1, we have this cosine part. Y2, we have the sine part. Okay? Yeah. Yeah. Here I skip some details. Yeah, but I understand some of you may feel how to follow the details. I skip it here. Yeah. But if you are interested in that details, I can put them at a, you know, to be further explanation number 2. Okay? Yeah. 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 So I can, you know, explain a little more. All right? Yeah. Using about 10 minutes to explain that part. Yeah. Okay? All right? Yeah. So here you can see the way we are doing here, 3 cases, similar to the way we did in the last class. Last class we did. So the version is slightly different. Y double prime plus A Y prime plus B, right? Yeah. This homogeneous. We also have 3 cases. Yeah. Yeah. The idea quite similar. Yeah. Yeah. All right. So you can see for relatively simple second order linear ODEs, we can find solutions. Relatively simple. Remember the general. Yeah. So here, let's recall the general. This is the general form of the second order linear ODE. But this general form, if P function and the Q function are relatively complicated, then we may not be able to find analytic solutions. Analytic solutions like these nice formulas, we call it analytic solutions. Okay? Yeah. All right. But, yeah. In later chapter, we can use power series method. The power series method. Yeah. Yeah. So we can find a power series solution. Yeah. Yeah. So we have, more tools we can use to solve this type of equations. Yeah. Yeah. And if power series method doesn't work, yeah, the last thing we can use numerical solutions. Yeah, numerical solutions. Yeah, the last thing. Numerical, yeah, we can always apply numerical solutions. Okay, yeah, approximation, yeah, not exact solution. Approximate solutions. Yeah. All right. B.2. Now, let's look at the existence theorem. Yeah, only the existence topic, but when we study that part, we look at the first order linear ODE case first. Yeah, because much simpler. Yeah. Then second order. Yeah. All right. First order linear ODEs. Yeah. Let's look at the existence topic. Yeah. Consider the initial value problem. Y prime equals f function. Yeah. Yeah. Here. So if I go back, yeah. So let's go back to the title, previous slide. Yeah. First order linear ODE, right? Yeah. But actually, here we do not require linear. Yeah. Actually linear. Yeah. But this function, yeah, this function could be arbitrary function. Yeah. Yeah. So here, yeah, because for the linear, regarding the y prime, that part linear, but regarding y, it may not be linear. For y, we allow y squared, so any kind of y terms. Yeah. Yeah. All right. Yeah. Let's look at a simple example. Yeah. Try to understand this problem. Yeah. The first equation, yeah, so very special. Yeah. Because here, the point of this simple example I want to show, the existence problem should be considered. Yeah. You cannot ignore existence problem, because sometimes the solution does not exist. Yeah. So this simple one, yeah, yeah, some very extreme case show you the solution does not exist. Yeah. Why? Yeah. Absolute value of the derivative y prime plus absolute value of y equals 0, and initial value equals 1. Yeah. Can you see this equation has no solution? It's very easy to see. Yeah. Because each term is greater or equal to 0, greater or equal to 0, but the right-hand side is 0. That right-hand side forces the two terms, each term of the left-hand side must be 0. None of the two terms can be non-zero. Right? Otherwise, this equation is not balanced. Yeah. Yeah. So it forces y prime equals 0 and y equals 0 everywhere. Not just at one point, everywhere. Okay? But your initial value violate that requirement. Your initial value y function at 0 equals 1, it's not, sorry, it's not a zero, not 0. Okay? Yeah, it's a contradiction. Yeah. All right. Then let's look at another simple first order ODE. Yeah. And then we all excuse me. We also want to see this existence problem. And this one is non-trivial. Yeah. Yeah. But the first simple example, it's trivial, right? Yeah. I mean, the existence problem of the first equation, it's trivial. Very easy to see it. But second one, non-trivial. Not easy to see it. Yeah. So let's study the second example. First, yeah, we can solve it. Yeah, because it's a simple, separable ODE. Yeah. We can use the separable method to find its solution. Yeah. All right. So we, find in this way. Yeah. Although you have absolute value, yeah, absolute value, but the constant part, you may have plus or minus sign, but this term is always positive, right? Here, this C star constant, a real number. Okay, yeah, we use a real number. So e to a real number, any real number, it's always positive number. All right. Then you have plus minus. That means your constant part could be arbitrary. Yeah. So that part, let's use a new constant, c, little c. This little c is arbitrary constant. Yeah. But the arbitrary constant, we like to make it a non-zero. Yeah. Non-zero. Okay? Yeah. Because if it's 0, then the initial condition cannot be satisfied, right? Yeah. If y equals 0, then the initial condition cannot be satisfied. So we require that little c constant cannot be 0. All right. Then, now we want to, further, try to explore a little more and see if the solution we found in this way is possible or not. The solution may not be available due to some reason, may not be available. Yeah. If it's not available, then you can realize the existence issue is important. Right? Existence issue is important because we try very hard. Finally, we find a solution, but later we realize the solution does not exist. No. All right, so let's take a look. Okay, all right. Because if this is a valid solution, let's assume if this is a valid solution, then you plug in the initial, this is the initial value. You plug in the numbers in the initial value, y of 2, when x equals 2 is 0, but your initial value is 1. So that's a contradiction. If your solution is like this, then it cannot satisfy the initial condition. That means the given initial value problem does not have any solution. So the existence problem Yeah, the answer is no. Not, no. Yeah. But another question, why this equation does not have any solution? No. So we need to find the reason why. Yeah. Conclusion, yeah, does not have any solution. But we want to see why. Yeah. Fortunately, we can see the answer quickly. Yeah. Let's look at the standard form of this equation. Yeah, standard form. Y prime equals f function. This is the standard form. Let's write in the standard form. So y prime equals the f function, right hand side. We write this is the right hand side. F of x comma y. Yeah, f function. Then, if you look at the f function, the denominator is x minus 2. Denominator cannot be 0, right? Yeah? The denominator can never be 0. Yeah? But your initial condition, you take the x value at a point that make the denominator 0. That causes the problem. Denominator 0 causes the problem. Yeah. All right, so we say this one. X equals 2 is not in the domain of a function. F function has its domain. It's not in the domain of the function, because in the domain, x is not allowed to be 2. Okay? That is the domain. Other than 2, all other x's are allowed. All other x's are allowed. So only this point, it's not allowed. That's the domain of f function. Okay? Yep. All right. But the point you take the initial value appears out of the domain. Out of the domain. Outside of the domain. Yeah. That's the reason your ODE does not have any solution. Yeah. Okay, yeah, so after these two simple examples, you can see we really need to get some formal result about this existence question. Yeah. All right. Now, existence theorem. The whole theorem. Yeah. So we won't prove, yeah, because this class is not math class. So we just understand this theorem. All right. The statement. Given the initial value problem, we define a neighborhood of the point. Yeah. Neighborhood, yeah. So in math, yeah, we need to use this concept a lot. What's the neighborhood of a point? Okay? Yeah. We need to draw a little disk. Yeah. Suppose you have a point, x0 and y0. The neighborhood, we mean it contains a disk around this point. Okay? Yeah. The neighborhood probably, you can have many shapes, but there is one little disk, you can find inside this neighborhood. Okay? All right. The neighborhood concept. Here, the neighborhood with this R symbol represent neighborhood. You can see it's a square shape. Actually, not square, rectangular shape. Yeah. Yeah. Rectangular shape around x0. Yeah. So here, let me draw draw the shape of this neighborhood. Okay, x0 here, y0 here. Yeah. So this point, x0, y0. Then rectangular shape. Okay, yeah. A, yeah. So because absolute value A, Y, B, B. Okay? So R is defined as this rectangular area. Yeah. All right. So in this area, F function has the following properties. First one, it is continuous at all points in R. Yeah, continuous. It's a continuous function inside this R area. Yeah. Second, it is bounded in R. Bounded function. So what's a bounded function? Yeah. Continuous function. Yeah. So use your calculus understanding. Continuous one. And the bounded function. Okay? There is a bound. You know? Upper bound, lower bound, there is a bound. Yeah. Later I will give you a definition. Yeah, so here, a bounded function. There exists a number capital K such that absolute value of this f function less than or equal to this k number. Yeah. Okay? Yeah. Then we call this function is a bounded function. All right. Yeah. All right. Then conclusion. Yeah. Under these two conditions, this initial value problem has at least one solution, y of x, in the smaller subinterval. See? Yeah. The solution, yeah, you can find a solution, but the solution should be smaller subinterval of, yeah. So the R, the interval is this one, but the y solution interval should be smaller than this one. How smaller? Yeah, the subinterval should be absolute value of this number less than alpha. There is another parameter alpha. Alpha should be smaller than a, little a. Yeah, alpha. So when alpha equals the minimum of a and a b over capital K. Yeah. Look at this theorem. Okay? All right. So in this theorem, yeah. Yeah. Why the conclusion is like this? See? The conclusion is like this. Okay? Yeah. So you need to reduce the existence part, yeah, so smaller subinterval, yeah, and how smaller, yeah, so you have, you know, minimum of those two numbers. So the reason, the conclusion looks like this, because it relies on the proof, the proof of the theorem. Yeah. In the proof, you require this condition in the proof. Otherwise, you cannot prove it. Without this condition, people cannot prove it. Only under this condition, people can prove it. So this conclusion relies on the technique of the proof, the specific technique of the proof. Yeah. Why I say this? Yeah. In math, many times, the results of the theorems rely on the techniques of the proof. If you change different way proof, then the result looks different. Okay? Yeah? So if you have advanced technique, you can get a better result. Yeah. All right. So that's very common. That's very common. Okay. Yeah. All right. Yeah. Checking the previous example. In the previous example, you can see now we want to use this existence theorem to see why it violates the two conditions. Here, we need to check these two conditions. First, continuous. Is this f function continuous at all points in R? Yeah. Okay? Yeah. Yeah, so this f function. Is this function continuous all points in R? No. But how can you see it's not continuous? Continuous at a point, no, 2 and y, yeah, y1, right? Yeah, here on y1. Yeah, because this y1 minus y0 is in this interval, okay? Yeah. Any y1, like that. But x must be 2, not continuous, okay? Yeah. Yeah. So that's the first condition check. Yeah. Second condition check, it's not bounded. Can you see it's not bounded? It's not bounded, yeah? So both conditions are violated. Both conditions are violated. Yeah. How can you see it? Oh, yeah, we are near the break time. Yeah. Yeah. So we use, quite some time. Yeah. Yeah. All right. Yeah. Because this theoretical part, we move relatively slow. Yeah. Anyway, yeah. Yeah, but here, I may like to explain a little bit, yeah, because for some details, rely on your knowledge of calculus. Sometimes you may not feel quite smooth, right? Yeah, quite smooth. Yeah. All right. So in calculus, how do we define continuity of a function? Continuity of function. Okay. Yeah. So here, let me explain. Let me use a simple graph to explain. All right. Yeah. So suppose at one point, yeah. So let me make this point x0. Okay. When I draw a curve, I use curve. Yeah, a curve. If the curve f function is continuous at this point, okay, all right. Not continuous, right? Yeah, from the shape of the curve, you can see this function is not continuous at this point. Yeah. But how do you represent? Yeah. So from the shape of the graph, you can see it's not continuous. All right. But how to use formula to represent this function is not continuous at this point. Yeah. The definition of the continuity concept is you take the limit from left-hand side. Left limit, okay? Yeah. Left limit. Yeah. We use this way. Limit x goes to x0, but from the left-hand side, we use, negative sign at the exponent position. That means left limit, okay? Left limit. This x. First, the limit must exists. Yeah. The first condition, the limit must exist. Second condition, the limit of x goes to the right limit, okay, plus sign, from the right direction. The right limit also exists. Okay, second condition. Third condition. Third condition. Okay, all right. These two limits must be equal. Equal. And it also must be equal to the function value at x0. Okay? Yeah. So the continuity definition requires these three conditions, 1, 2, 3, in calculus. If you miss any one, it's not continuous. Okay? Yeah. If you miss any one, it doesn't, it's not continuous. Okay? All right, so here, I'll give you the definition so we recall, okay? Yeah. So we try to understand a little better. Yeah. All right. Now, let's take a break. So when you come back at 7:10, okay? Yeah. At 7:10, I want to use this definition to explain why this f function is not continuous at this point. Okay? Yeah.